Yeah, it's my pleasure. My pleasure to introduce Professor Xiangdong Ji from the University of Maryland. We share part of our pedigree. We were both at Caltech and MIT at various times. Xiangdong, if you study QCD factorization, TMD physics, you will see Professor G's name a lot. So one of his most exciting advances in recent years is the proposal of a way to actually perhaps compute PDFs on the lattice in a certain limit of QCD. And I think that's a big part of what we'll talk to you about and tell you about TMDs and large momentum effective theory. So it's all yours, Xiangdong.
Thank you, Chris. Thank you very much for the invitation. And I really wanted to come to meet all the people here, but unfortunately that I have health issues which are not good kind of health issues for the COVID. And so so my wife really strongly against my going. And but any case that I'm happy to deliver these lectures online. I'm gonna talk about the TMD. This is a TMD school, so therefore I'm going to talk about the TMD, large moment effective theory. I have worked on TMDs for many years, good part of the 20 years maybe, and I have not my main topic to work on. It's kind of a side project, but I think it get more and more interested in recent years. So I could explain to you why. And my main concern is how to calculate TMDs from lattice. Okay, you heard already the first lecture by Fiala, and she already gave you some flavors of lattice calculations of TMD stuff. I try to explain this from a very basic point of view. So let me give you some references to start with. First of all, there's this overview paper written by my postdocs and students and collaborators, which is published in the Review of Modern Physics last year. Now, some of the key references refer to lattice calculations of TMDs. I think the first here, I'm only referring to the work that I did over the years, and first starting with the 2013 paper, then 2014. Then we had a couple of PRD papers, 2015, 2019. So that was like in dark ages. We tried to searching for ways how we can do calculations on lattice. The final, I think, the breakthrough happened in 2019 with two of my postdoc, two Lius, and we still had a paper in nuclear physics B and physics class B. Notice I have not listed the papers from MIT group and by Yongqiao and Stewart. I'm sure you have heard a lot about those from Ian's lecture. And I'm not going to talk about the work from German group and Engelhardt at all. And he's going to give tomorrow a lecture on this. And so these are the references. Now I'm going to switch to my notebook and try to lecture from the in a whiteboard. Okay. So first question I want to talk about, what is a parton? What is a parton? I'm sure that every one of you have been working on partons for quite some time. But what is a parton? And there are at least three different ways you can think about partons. One is defined by QCD factorization theorems. And so these are the work by like Collins and Super, Sturman. Okay, you heard this name a lot. Then also this soft collinear effective theory. Now in this framework, the parton distributions are like correlations. So here you got time here, maybe time here and space here. So partons are correlation function along the light cone. Okay, so you can write operators this direction called n, and so it's a correlation function in the n direction with the Wilson line in the middle in the proton state, and you calculate Fourier transform with respect to the light cone distance, and then you got a Parton distribution. All right, so that's the definition number one. Definition number two, the partons are defined by a bunch of twist-2 operators. Okay, and this is in a textbook by Peskin, so I'm sure a lot of you knows about the Peskin field theory. And so you define a set of twist-2 operators with the indices. And so you got a sidebar, gamma mu1, ID mu2, and a bunch of derivatives. You symmetrize and traceless, you calculate the matrix element, you construct a Parton distribution out of this. Okay. Now the third method is what you heard from, for example, Stan Brodsky's talk. Okay. And in which that he has what's this thing called a light-front quantization. Okay. Light-front quantization. And so partons are the quanta which appears in those light-front quantization. All right. So you can have a wave function, light-front wave function, that you can calculate the Parton distribution, the ADAC A. So that's the three common definition you would hear a lot. However, that in the next hour, I'm going to talk about a different definition of partons, Feynman's definition. Okay, and this definition people pay the lip service that in their introduction of Parton models, but never developed to the point which you can actually find some use, you can do something useful with it. And so let's talk about what is the Feynman's definition. Consider, for example, a hydrogen atom with a proton with the electron moving around. And so therefore you can solve this as a wave function, psi r, after solve the Schrodinger equation. And then you can make a transformation to momentum space. And so this is the Fourier transform to the momentum space. And you got a momentum space wave function. After you got a momentum space wave function, you can define a momentum density, which is the psi squared, okay, in momentum space. Okay, so this is the momentum density. Let's call it MD, because I talk about the momentum density a lot. And if you expand, you plug in this formula in here, you work this out, then you discover that this momentum density is the integral of two coordinates of capital R and small r. A small r is the relative separation of the two wave functions. And so therefore it will be the capital R is the center of mass of the two wave function amplitudes. The little r is the separation of these two. So this again, the coordinate space hydrogen atom wave function. But it turns out that this combination here, that is the wave functions split in the space and Fourier transform with respect to the separation. And this is called the Wigner distribution. A Wigner distribution as a function of R and K. Okay, so the center mass R and the relative coordinates is transformed with respect to K. So this is the Wigner function. Okay, so the momentum distribution is nothing but an integral of the Wigner function with respect to the R. So you can even picture this. So this is R plus R over 2. This is R minus R over 2. This is center mass. And then you got a psi star here and psi here. Okay, so you got to basically you're calculating a correlation function in coordinate space. And then if you Fourier transform relative to the separation, you got the K. And this K will give you the momentum distribution, okay? And in fact, the Wigner distribution is a phase-space distribution, and it can use to calculate any kind of quantum mechanical operator depending on the position and momentum. So you just average over the phase space, and you got a quantum mechanical average. So this is what, so quantum mechanical average of any operator as a function of position and momentum can be calculated as a weighted with a Wigner function. Is there a question somewhere? Okay, so far that I consider the hydrogen atom is at rest. Everybody study hydrogen atom at rest. But the problem is what happens if you let it move? So I have a hydrogen atom is moving in the z direction with some momentum pz. And then you ask, what is the wave function for hydrogen atom? The answer is presumably going to also depend on the how fast the hydrogen atom is moving or what momentum do you have. And in this case, you can define a momentum density going to depend on how fast it moves. So therefore, you have a wave function squared and depend on the center mass momentum pz. And once again, you can write this out as a wave function of r minus over 2. But now this wave function have a fixed center mass momentum pz and fixed center mass momentum pz. This guy gonna be r plus r over 2, then e to the I k dot r dr. Okay, so here I introduce the fact that for a moving system, its wave function gonna have a dependence on the center mass motion, and momentum density could be different. Okay, it could be different. And how do you do this? Actually, it's not an easy thing to do, okay? Because you need to study relativity and how do you transform the wave function. And I'm gonna come back to this point later, that how do you obtain a wave function when hydrogen atom is traveling, okay? But before I do this, let me try to move this concept to field theory. You learn a lot of QCD now, so you're familiar with the quantum field theory. So how do I move, to translate or transform these concepts or translate those concepts into quantum field theory? Okay, well, it's very simple, in fact. You replace the wave function by operators, and then you average in the states with some momentum pz. So therefore, in this case, with the Hadron, you assume have momentum pz. And then you have a field operator, which is now r over 2. You see, it in principle, it depends on the center mass, but because of the translational invariance in quantum field theory, in fact, the r dependence actually disappears. Okay, you can use the Heisenberg equation motion to translate those operators in space, and then you discover you calculate the forward matrix elements. This center mass dependence actually doesn't matter, and so from now on, I'm going to omit the capital R dependence. So therefore, now you have a psi star. I'm going to write it in think of a Dirac fields, write as a psi bar, then gamma 0, then psi r over 2. And then I need to Fourier transform relative to the separation. Okay, so I get a momentum distribution in a Hadron as the expectation value of these correlation operators in the states with definite momentum pz. So now I have a momentum distribution look like this. Okay, and so this is one part that is jump from the first quantized theory to second quantized theory. So I have those psi as a fuse operators. But I have another problem. That is, we're dealing with gauge theories. And so gauge symmetry is very important. I know that these psi's at different points, they're going to transform differently on gauge transformation. So therefore, I need to stick in a Wilson line between the 2 points, the minus r over 2 plus r over 2. So I'm going to stick in the Wilson line, minus r over 2 plus r over 2, to make this gauge invariant. So here's minus r over 2, here's plus r over 2, and let's make a Wilson line like this, all right? So, and then that you presumably have a gauge invariant definition of momentum distribution. Now, what kind of Wilson line you're going to choose is going to depend on the experiment. Okay, so experiment determine what the Wilson line should be. You can calculate the momentum density, the infinite number of ways to define momentum density by choosing the Wilson line. But if you compare with the experiment, this particular experiment has a Wilson line, and so therefore you can choose there. Okay. And then, so let me make a little more clean here. So you have a momentum distribution depend on the center mass PZ and Fourier transform again with respect to the separation with a plane wave state and with a psi minus r over 2 with a Wilson line stick in the middle with a gamma 0 and then r over 2 PZ. So this is the momentum distribution in the quantum field theory. Okay. Now, I'm going to talk about TMDs later, but for a long time, we will not talk about TMDs because all the stuff I want to build up in the machinery in the end, which is good for TMDs, all right? So to build that machinery, I'm going to consider that to integrate out the transverse momentum dependence, because I have a direction called Z. The hadron is moving in the Z direction. So I have a longitudinal direction called Z, a transverse direction, presumably called X and Y. And so I'm going to integrate out the K dependence in the transverse direction and define a momentum density, a reduced momentum density, only depend on KZ and PZ. Okay, so this is the momentum density in the hadron. And if I do that, and then I will get, you know, this is very easy to go there and integrate, and you discover that you set the transverse coordinate of r is equal to 0, and so therefore you can now end up with integration dz, ikzz, and then you have pz and psi minus z over 2, and gamma 0, w z over 2, and pz. So you can see the correlation now is it at the direction of motion, okay? Along the direction of motion, z over 2, sorry, I should have actually psi here, and w is a Wilson line, and so the most natural choice, now I have basically 2 points along the z direction. This is the z coordinates, minus z over 2 plus z over 2. The most natural choice, of course, is just a straight line. So the Wilson line can be just a straight line here, okay? A straight line. And for the rest of the discussion, I'm going to only choose the Wilson line as a straight line. Okay, so now you have this definition of momentum distribution in field theory. So what it look like? So let's consider, for example, a hadron at rest, pz equal to 0. If pz equal to 0 and as function of kz, presumably you have a momentum distribution peaked around the kz equal to 0 and then decays away when the kz gets large. And so here, the width here corresponds to the inverse of the size of the hadron. So you get a momentum distribution look like this. Now, what happens when the hadron moves? When the hadron moves, and then this, let's assume it's a kinematic Lorentz boost. And I boost every one of the constituents with the momentum. You add up, just to add a certain boost the momentum to that. And so therefore, presumably this peak is getting shifted along the direction of motion. So now this is pz not equal to 0. And then its peak is around some value lambda, but it looks like this. So this is called a kinematic boost. And this is very simple, right? But in real life, this is not the case. And because the boost is dynamical, okay? And I can explain what does it mean in a minute. And because the boost is dynamical, so therefore the momentum distribution actually doesn't look like this at all. It will, in fact, instead of going up, it will fall much faster when the KZ is bigger than certain average momentum lambda. And then this guy actually doesn't fall as fast and fall much slower than before. So we'll get something like this, okay? So this is the dynamical boost, okay? So when you do a dynamic boost, you get a distribution look like this. Now, the boost operator, which you usually call a KI, there's 3 boost operator, 1, 2, 3, because you can boost in 3 different directions. And also you got a rotation operator generator as angular momentum operators. And together they form so-called a Lorentz group. Okay. So Lorentz group consists of rotation plus the boost. And the JI is interaction independent. I put a question mark in here because the magnetic fields actually mess us up stuff. But let's assume you don't have any magnetic fields, and so therefore the angular momentum operator is always interaction free. However, the KI is fully dynamical. The boost operator is fully dynamical, meaning that it has the interaction dependence. Okay. So what does it mean by interaction dependence? Think of a Hamiltonian. The Hamiltonian depends on interactions, right? The boost operator is just as complicated as the Hamiltonian. All right. So it means that if you wanted to solve the boost, this is going to be terribly difficult. Okay. So suppose, for example, you have an operator at 0 momentum and you want to boost this with some kind of eta k and minus eta k. And these are the, the boost into some kind of other momentum using the Heisenberg equations of motion. And k is the boost operator, eta is some kind of rapidity variable. And so now if you try to solve this equation, you can derive a Heisenberg equations of motion for the boost. So now you have a calculated commutator of O with the boost operator. As I said, the boost operator is dynamical, and so therefore solving this equation is same as solving the time-dependent Schrodinger equation. So in other words, the boost is terribly difficult, okay? It's terribly difficult to make the boost. And so therefore it means that suppose you know what is the momentum distribution at when hadron is at rest, or for hydrogen atom for that matter. If you wanted to know what is the momentum distribution when hydrogen atom travels at 0.5 speed of light, the answer is you don't know how to calculate. It's very difficult to calculate. And boost is very hard. Okay. Now, let me talk about Feynman's idea. By the way, that I had a good fortune to listen to Feynman's lecture when I was a postdoc at Caltech. And he was teaching a course in QCD, basically. And without, I think he's really, great physicist, and the lectures are very interesting and all that. Okay. So Feynman's idea is that so long as PZ is much greater than hadron scales, like lambda QCD or the mass of the hadron, then the momentum distribution Kz Pz should be similar. Okay. And which let me call that large momentum symmetry. Okay, large momentum symmetry, if you like. So the argument actually is very simple. It says, well, let's imagine if I have a momentum distribution like this, I can try to expand it as when Pz go to infinity. And so therefore I would have a distribution of Pz equal to infinity. And what it could be expansion parameter going to be? The answer is whatever other scale you have in the Hadron divided by Pz. And so for the reasons of parity, and so it should be coming with squared. And so therefore with the first derivative and then to the fourth and to, so you can see that you got a small parameter, which is the m divided by Pz. So if m is on order of a GeV, so if Pz is very larger than the GeV, then all of this should be negligible. So therefore, the momentum distribution of in a hadron should be similar. Okay, and so that's the symmetry. So doesn't matter whether your hadron momentum is equal to 10 GeV or 100 GeV or 1 TeV or 10 TeV. All the momentum distribution should be similar. This is the large momentum symmetry. Okay. And this is basically a dimensional analysis. Okay, a dimensional analysis, right? It kind of dimensional analysis basically is a what else could be argument, right? What else could be? If you're trying to expand it around Pz equal to infinity, and what kind of expansion parameter you can have, the only thing you can come up with something is the hadron mass divided Pz, and so therefore that's the only thing can come up. And so therefore that if the momentum is large enough, even though that boost in the hadron is very difficult, but I know that when you go from 10 GeV all the way to 10 TeV, the momentum distribution shouldn't change very much. Okay, so, and then that Feynman defined Parton distributions.
Hey, Xiangdong, can I ask a question?
Yes.
Maybe I didn't pay attention. Can you remind me what are the two arguments Kz and Pz mean again? What is the difference between Kz and Pz?
Can you repeat the question again?
What are the two arguments Kz and Pz? I just didn't pay attention.
Oh, Kz is the momentum of the constituents, like electron in a hydrogen atom. Pz is the momentum of the whole hydrogen atom or whole hadron.
Okay. So that you're saying the distribution in Kz is invariant, has this large momentum symmetry. When Pz becomes large, the distribution in Kz stays roughly the same.
Exactly.
Okay.
That's the argument. So now we're going to define the Parton distributions. That is, so let's define the moment the Pz go to infinity. A hadron traveling at the speed of light, v equal to c. And in this case, that all the Kz going to go to infinity. So let me define the ratio of Kz over Pz is equal to x. And in the limit of Pz go to infinity and Kz go to infinity. Okay. And then that the Parton, so in this case, I get a Parton distribution. N of x, which is 1 over Pz, d lambda e to the lambda x, and infinite momentum hadron state. Then you have lambda over 2 and gamma 0 w psi lambda over 2 and infinite momentum state. Okay, so basically the Feynman Parton distribution is defined as a momentum distribution in a state or in a hadron moving with infinite momentum or traveling at the speed of light. This is the Feynman's definition of partons. Okay, Of course, that you learn this, I'm sure, that the first time Parton model was introduced, it was stated in such a way, but you have never seen a formula. And people don't usually write down a formula like this, okay? However, that there is a problem with this, okay? There's a problem because we're dealing with the quantum field theories. In quantum field theory, you can see that this argument doesn't work, okay? This argument breaks down. Okay, let me tell you why it breaks down. Remember that the Feynman has this idea that when the PZ gets very large, that the momentum distribution should go like, have an expansion in M over PZ square. And so therefore, it should reach to a limit. Okay, this is the Parton limit. However, turns out this is not true in quantum field theory, because Feynman was not really discussing quantum field theories. He was talking about some kind of narrative quark model. Okay, narrativistic systems. Okay, so all that argument of Feynman doesn't work in quantum field theories for the following reason. That is, you see that this dimensional analysis says that a dependence should be in power, but it turns out there's logs. Okay, this logs gonna break Feynman's argument. So if you try to calculate, for example, how does the momentum distribution gonna depend on the PZ? And you discover that when PZ gets very large, this thing can be calculated in perturbation theory. And you discover that the perturbation theory is gonna give you log of PZ over mu, and RFS square, log square, PZ over mu squares. So therefore, literally that when PZ goes to infinity, that limit really doesn't exist because you have logs. However, you can turn that dependence into a renormalization group equation in PZ. That is, you can write down the momentum distribution as a function of PZ. How does it depend on this? So you're gonna get log PZ. It turns out that this you can write down a typical renormalization group equation looking equation with some gammas which can calculate in perturbation theory. Then you got an n. Okay, so this is the kz here. This is integration of a kz prime, pz, and dkz prime, and then you have gamma depending on k and kz and kz prime. So in other words, the dependence of the n, even though one can calculate in field theory by looking at the renormalization group equations, and so therefore that it doesn't really goes into a limit very smoothly. Okay, there's no smooth limit. So in other words, the n go to infinity does not have a well-defined limit. Okay, and it does not have a well-defined limit due to the UV divergence. And in fact, the reason that it doesn't have a well-defined limit because the field theory at the UV behavior is pretty non-trivial. And in fact, that you can ask the question, suppose I have a UV cutoff in here. So when you PZ go to infinity, whether you do that before this guy goes to infinity, or you do it after and goes to infinity. So which order are you taking when you take a PZ go to infinity? All right. And so in field theory, you have to think about UVs. Okay. Now, the Feynman's picture, of course, is to think about this limit. Originally, okay. So let me try to restate what I'm trying to say here. So you have two different kind of limit you want to do. The Parton model is actually corresponding to this limit. This is called a Parton limit. That is, the PZ is much greater than the UV cutoff. Okay, so in other words, you take in PZ go to infinity without thinking of the UV cutoff. Whereas the ordinary momentum distribution that I described so far is this limit. That is, you always have to calculate with the momentum PZ much, much smaller than UV cutoff. So these are not the same thing. Okay. And because of UV divergence, you have the ambiguity. Okay. So now let me restate again. Partons, okay, are defined as, okay, or Parton or PDFs, Parton distributions. PDFs are defined as defined in the limit of PZ go to infinity, disregard the UV divergence. So therefore, you don't regulate the theory, and then you take PZ go to infinity first, you define the partons. So therefore, this is really not in the original theory, not in the original theory, because in the original theory, you everything have to define UV cutoff, and then you define it. So therefore, from that point of view, the parton is an effective objects, not okay, not a physical object. Okay, and so this concept of the this concept of taking limits is very much like heavy quark effective theories. The heavy quark effective theory, for example, when the B quark mass gets very large, you can take a B quark mass go to infinity, but you take the limit, disregard the UV divergences, and so therefore you end up with an effective theory. So therefore, partons, in fact, are the effective theories. So partons defines the effective theory. So nobody tells you this. In fact, you know, in all the textbooks, nobody talk about it this way. And partons are actually ideal objects, doesn't exist in the real world. Okay, so let me now try to impress you with a calculation to show you the point. Okay, and suppose, for example, you want to calculate the self-energy of a particle with a momentum pz moving in certain direction, and you have the radiated correction. So you want to calculate a one-loop self-energy correction to this particle. And so therefore, the self-energy, you would integrate over the momentum. And so therefore, you have a propagator goes like 1 over k squared. This is presumably is a gluon or photon, whatever. And then you have a propagator for the fermion, okay, p plus k squared, and let's assume it's massless, and so therefore it doesn't really matter. Okay, so you have a Feynman integral, look like this. And there are two ways you can carry out this integral. The first way is the way that what original theory asks you to do is you do the integral first. Do the integral first, and you will see that this integral will generate you some log dependence on p's. Okay. However, you can do the effective theory. The effective theory is, which is not the original theory, but will make sense look simple, and that's what a Parton model concept is. That is, you take PZ go to infinity under the integral before you do integral. And the reason that why do you want to do this? The reason you want to do this is that you want to realize Feynman's idea that the whole thing is independent of PZ. Okay, and in reality, we know it has log dependence, but let's just forget about the log dependence. I wanted to create an effective theory which is independent of momentum PZ. And what do? Well, you try to take the PZ equal to infinity first. And in this case, the whole integral going to be independent of PZ. Okay. So let me show you how to do this. All right. So you're going to take a PZ equal to infinity first. So if you take PZ equal to infinity first, your momentum is going to be some kind of large number and 1, 0, 0. And if you're traveling in the Z direction, is 1, 0, 0, 1. Right. So this is a Lycon vector you've seen many times in those lectures. And the particle is traveling in the Z direction. And so now let's do this. Let's do the denominator. The denominator of the P plus K squared. It would be P squared plus 2P dot K plus K squared. And P squared is very small, it's 0. So therefore, I only consider the P dot K part. So 2 lambda. And then I have a K0 minus KZ plus K squared. And now that my lambda is really going to infinity because my momentum gets very large. So in this case that I can neglect the K squared because I'm taking infinity under the integral sign. So therefore this guy is going to become 2 lambda of K0 minus KZ. All right, so now I'm going to stick this denominator back in there. So my integral become d4 of K, 2 pi to the 4th, 1 over K squared. Remember that I was doing the denominator as like P plus K squared, but in reality, I have another P plus K in the numerator, which is useful because it helped me to take the lambda go to infinity limit. And so therefore, I would have in the denominator will be 2 lambda, K0 minus KZ. In the numerator, I can neglect because my P is really getting very large, I can neglect the K. And so therefore there's another lambda from the P over there, and the Lycon vector n slash, let's call it, yeah. So, and then lambda cancels, and now you have an integral, which is d4 of K 2 pi to the 4th, and 1 over K squared, and goes like K0 minus KZ. You can see that this thing now is entirely independent of PZ, right? Just like realizing the large momentum symmetry in this way, all right? So you can realize the large momentum symmetry with a price. The price is that now this integral is linearly divergent. So you altered the UV property of the system. This has a linear divergence, okay? And the original only has a log divergence. So you mess up the UV part. And so therefore, the partons, you see, only this way you can get partons. So the partons are effective objects and they have to be defined. They have to be defined with UV specifications. Okay, so parton are not a physical objects, so you have to define a UV specifications because you altered the UV property of the original theory. And so that's why when we talk about partons, we always have to say MS bar, or whatever, And so the MS bar is a way to regulate the partons, the UV properties. And but that's okay. And that's a convention. If everybody likes to use MS bar, that's fine. You just compare calculations in the MS bar scheme. This should be fine. Okay, so let me stop here entertain some questions because I have talked a lot and probably a bit faster than I have planned to do because I thought that, I have prepared too many materials and so want to go fast, but it turns out I do faster than I intended to. So I have a lot of time for you to ask questions. And okay.
Time for questions.
Since we are working in TMD, you integrate over KT right in the beginning.
Yes, I only consider so far a distribution with the KT integrated.
Exactly.
I will come to the point where without integration later on. Obviously, I have to do that because, yeah.
My point is once we integrate over KT, that means what KT is 0, right?
What do you
So-
mean KT is 0?
I mean, when we integrate over KT, that means we don't have any dependence on KT, right? So far, after the-
Everything has no KT dependence has been integrated away already. KT dependence have been integrated. Sorry, that I need to bring back my screen. I don't know how to do this. Okay, here we go. Yeah, the KT dependence is entirely integrated. So I'm talking about a collinear Parton distribution, if you like.
Okay, so we still have KT dependent.
Yes, I will talk about a KT dependence in a moment. Because the way that I set up is such that later on when I talk about KT, everything seems to be very natural. Okay. So if I understand what I'm doing here, then the KT part will be straightforward.
Thank you.
Andrew?
I think I just misunderstand something with the switching of the limits. So it sounds like you were saying that because we're not doing the momentum integral first, we're taking the PZ limit first. That's what makes it an effective theory. Is that what you're saying?
Yes.
Okay. So,
Because the original theory, I'll ask you to do the integration first. And that's the original theory. But if you do this, you end up with a log dependence on the P. However, the large momentum symmetry is to say, well, I don't want to have any P dependence, right? So I have a symmetry, different system with different momentum should be the same. And so therefore, what I do is I'm gonna take the P is equal to infinity limit first. If I take that limit first under the integral, and then I realize that symmetry, because it doesn't matter how big the lambda is, whether lambda is equal to 10 TeV or Planck scale, you should get the same answer because it cancels numerator and denominator, right? So you realize the large momentum symmetry, but with a price. The price is that you alter the UV property of the system, okay? And so originally log divergent integral all of a sudden becomes linearly divergent, okay? So which means that whatever you're doing afterwards is not the original theory, okay? It's an effective theory. It's an effective theory which you have to impose renormalizations by itself. And so now it's up to you. You say, okay, I do MS bar, or I do lattice cutoff, or do whatever kind of harder cutoff. And so now the theory, in a way, is not a UV control.
So in the original theory, I think it's the terminology that's mixing me up. When you say taking the PZ to infinity limit first, you're not saying in the original theory you would take the PZ goes to infinity limit at all, right? It's restricting that phase space that you're considering that makes it the effective theory. I think I was just
Can I
misunderstanding
answer?
that.
Let me try answering give the same answer a different way. Because yeah, in this school last week, we had some lectures on effective field theory.
Mm-hmm.
And so when Xiangdong says, take the PZ to infinity limit first, that's like, take your QCD Lagrangian and do a power expansion of it in the limit, this propagator is infinite Z momentum and it's emitting softer things. And if you construct the Lagrangian first before you compute any integrals, loop integrals, Feynman diagrams, like you'll get the Lagrangian, basically of SCT actually.
Oh, okay.
And then the integral he has, where we just have the Ks with no PZ dependence, is basically that's like the Feynman rule you would get for that graph in that new theory you constructed with that new Lagrangian.
Okay.
So so strength same thing, but here just discussing the level of the integral.
Gotcha. All right, thank you.
And on that note, maybe the follow-up question I would ask is, in the way you described this, Xiangdong, where would, yeah, you said you take this limit and then you said you change the UV behavior, yeah, which is clear. Where do we see that you didn't change the lower energy behavior? The behavior. Where do you see that you still get the right
This is
answers
an
that the
excellent
original
question.
theory? would-
This is an excellent question. What you should see is that the infrared property of this diagram is independent of whether you take a p go to under the integral sign or outside the integral. So the IR property does not change. Okay, does not change. And this is very important. All right. And that you have to show. You have to show that order by order in perturbation theory, that the IR property is still the same.
Arthur has a question.
Yeah, in the definition of the number density, is there a reason why we choose gamma naught as opposed to gamma 3 or gamma plus or any other gamma matrix?
That was just it was just a motivation from the narrativistic theory, because the narrativist theory, when we talk about a number, you know, we talk about, you know, the numbers that relate to J0 is the time components of the current, give you the number.
Thank you. Question in the back, you might have to come up here.
Yeah, so I saw that you had a paper about the light front being an effective theory. So is the argument that you just take, you can translate this infinite momentum approach and then translate it to the light front?
This is a great question. In fact, I was going to write a paper on that, but maybe I just write that in the notes. So what is the light front quantization? Light front quantization is simply the infinite momentum limit with PZ taken to infinity before UV cutoff is imposed. Okay, and this is in fact in the original paper in 1966 by Steven Weinberg. He just take Feynman rule and boost to the infinite momentum frame and gets a bunch of new rules and then calculate. This is light front quantization. So then you need to, so then you change the UV property of a theory. And so you want to solve this very singular theory in a light front quantization. And it turns out that it's extremely difficult, if it's not impossible. So far, I don't think anybody has any clue how to solve that terribly divergent theory.
People on Zoom can ask questions also. Raise your hand and we'll let you unmute.
Okay, if no more questions, I can press on with my lecture. Is that okay?
Yeah, if you're ready to press on, go ahead. If you need a few minutes break, you prefer a few minutes
I
break.
can. The scheduled break happens at
Yeah,
3:30, right?
yeah, we're going to have coffee in 35 minutes.
Yeah.
But-
So I can do another 35 minutes lecture.
Okay, go ahead.
Okay, good. So now I'm gonna try to compare this definition of partons. So now I'm gonna, again, let me remind you the Feynman definition of partons, okay? The the Feynman definition of partons is that you take you calculate the correlation function in space in this hadron with momentum equal to infinity. And then you have this, let's say you have the W and psi lambda over 2 and P infinity. So what is lambda here? Lambda is equal to ZPZ. Okay, so you take the limit in a very, very careful fashion. That is, you let P go to infinity, but you also let the Z goes to 0. PZ go to infinity and Z go to 0, but you let lambda, which is the product of PZZ is equal to lambda. And lambda kept as a finite. And then you integrate of your Fourier transform with respect to the lambda. And that conjugate give you the Parton momentum. So this is the formula. If you use literally the Feynman's idea, calculate partons, and then also you take a PZ again, the PZ go to P go to infinity before you apply any regulator. Okay, PZ go to infinity before you apply before UV. Okay, so I'm very proud of this formula because nobody has in the literature, you found nowhere does formula, that formula exists. So this is literally the Feynman's idea, put it into the quantum field theory. And you will see that the beauty of this formula is that it's entirely equivalent to the definition I told you before, and entails a new calculation of methods for the lattice calculations. And so let me try to explain to you why this formula is so beautiful, okay? First of all, I want to show this formula is exactly the same as the Collins, Soper, or you know, Bauer, Stewart, Lycon correlation formula, okay? And it's very easy to show, in fact. So this is show the equivalence. Equivalence to standard factorization formula, okay? And so let's see how that happens. You see that I have a momentum which go to infinity. I can imagine this is equal to a boost of infinite boost, which I will call as a lambda, and with the infinite boost, and with the momentum started from a hadron with the momentum equal to 0, I applied infinite boost, I got infinite momentum, right? Now I can also argue that you can also start with a hadron of any momentum and apply infinite boost, but this momentum is finite. And this why I call the residual momentum, right? So this is a, you know, whatever you can start with some finite momentum and you boost it, give it infinite boost, you get infinite momentum. So therefore you can get infinite momentum with the infinite number of ways, all right? And it's useful to think about that you have a residual momentum because later on we will have the residual momentum symmetry. Okay, the Feynman's large momentum symmetry, in the end of the day, become the residual momentum symmetry. I will talk about a little bit of a residual momentum symmetry later on. And so if I do this, what happens? So here the Parton distribution now becomes d lambda over 2 pi e to the I lambda x. Then I will have some residual momentum. Okay, if you like, you can put a res in there, represent the residual. And then you have an infinite boost on an operator with an infinite boost with the residual momentum. And so now you have a operator. So now you're going to have a now you have to boost this operator. This is the boosted operator is equal to lambda infinity, O, and this. So what is this operator? This operator, remember that I told you that these are the correlation functions in the z direction. So this is z direction, this is time. So the operator gonna start with, remember, minus z over 2, z over 2. And I have a like cone gauge length along the z direction. And so this is this composite operator, all right? So this is this operator with the psi here, psi bar here, whatever, okay? And so now we're gonna apply a boost to this operator. You wanna say, how do I boost the composite operator? Well, you have to work through Peskin and Schroeder and tells you how this operator boost works. And so I'm gonna just tell you what the answer is. If you apply an infinite boost to a segment of line here, the Wilson line, and what happens is that this guy gonna go try to hug the light cone. And this guy gonna go over there to hug the light cone. So in the end of the day, when you do apply the infinite boost, you simply become a correlator along the light cone. By the way, you become a light cone correlator here, and this is now going to be lambda over 2, whatever that is. I'm gonna very, very hand waving about my sign here, okay? So let's call it minus here and plus here, okay? So it becomes a light cone correlator. This field's now gonna live on the light cone. Okay, so which means that now I have a formula after you boost. And so let's call this direction N. So therefore this is equal minus psi bar minus lambda n over 2 and W. And I have to boost the gamma 0. If you do that, get the gamma plus. Okay, the infinite booster will give me gamma plus. And then you have a psi lambda n over 2. And then you have a residual momentum, and you have the residual momentum and e to the I lambda x integrated. And this guy is in fact independent of the residual momentum. In other words, you have a light cone operator here, and any state that you calculate, it will give you the same answer. So that's the residual momentum independence. As far as I know that this formula appears in the paper by Collins and Super and back in 1970s, maybe early 1970s, okay? So this is the standard light cone distribution or momentum distribution, okay? However, that this is what appears in textbooks and papers all the time. But there's a problem. The problem is that this is a light cone correlation function. And so therefore it has a real time dependence. And this appears one time, this another time. And so you would have to simulate quantum field theory with real time dependence. And so we don't know how to do that. And there's no classical algorithm allows you to simulate the time dependence. Okay. And nowadays people think about a quantum computer. And in a quantum computer, people believe they can calculate the time dependence. However, that I don't know whether I can live to see that or not. And I mean, you know, for QCD, right? And so you can always cook up a very simple 1+1 dimensional theory, solve time dependence and be happy. But this is still a lot far away from solving QCD. So in any case, that because of this light cone dependence, and nobody knows how to put that on the Euclidean lattice to do lattice calculations. So what people have done instead is to look at the moments of this Parton distribution. So you look at the moments and you integrate over the x from minus infinity to plus infinity. In fact, in practice, it's a -1 to +1 because that's only the support that you have. And then if you do that, if you look at this formula, and basically your Taylor expand the lambda around the lambda equal to 0. When you Taylor expand and you calculate the moments, and then you got an m1 and mu1 and mu to the n, and you got an operator mu1 to the mu n. You got a local operator, and this local operator is just psi bar gamma mu1, id mu2, and id mu to the n, and bunch of derivatives acting on size. And this now has no time dependence. Okay, this has no time dependence. This is twist 2 operator. You can calculate it on lattice because it has no time dependence. And so that's called a moment calculation on lattice. So people have been doing this for years, since 1980s, I think, 1980s, since the 1980s. So people have been doing moment calculations. But the problem with the moments is that you can only calculate so many moments. The reason is you have so many derivatives. Okay, the derivatives. The derivatives become extremely noisy when you have more and more derivatives. And in fact, the most of the calculation only calculate up to n equal to 3. I have not seen anybody calculate n equal to 4. So this moment calculation. So with 3 moments, can you really calculate the Parton, reconstruct the Parton distribution? That is terribly hard. Okay, so calculate the try to calculate this is very difficult. Okay, and so you can see that with these Parton distributions, we wanted to calculate it in lattice, and I say, well, the Lycon correlation doesn't work because of time dependence. The moment calculation does not work very well because you can only do n1, 2, 3. So what are the alternatives? The alternative is what Stambrowski and Ken Wilson come up with, so-called a light-fine quantization. Okay, so what is light-fine quantization? Okay, LFQ. The light-fine quantization is carried out in the A plus equal to 0 gauge. Okay. And then in this context, you can look at the light cone. Again, this n, this is p, this time, this is space. And light-fine quantization means that your initial data plane is here on the light cone. So therefore you evolve the system along the x plus direction. And this is the x minus direction. So you have the initial data on the x minus, and then you evolve in x plus. And so this is called a light-fine quantization. So therefore you postulate a commutation relation like a psi 0, psi x minus at fixed x plus. So therefore it has to be x minus and x perp, and this become some kind of delta function, and then x perp, and then you have some kind of, I don't know, some kind of epsilon function in x minus. And so you postulate the quantization condition like this. Instead of equal real time, you postulate the quantization in terms of the Lycon time. And then your fields can be expanded at an equal x plus equal to 0 in terms of a creation annihilation operators. And these are what I call the quanta in the light-fine quantization. They're Parton creation annihilation operators now. Okay. And so then you can write the Parton distribution simply as in some residual momentum states, P, and then you have A dagger, XP, and K perp, and AXP K perp. So now the Parton distribution are really a number of operators in the light from quantization scheme, but you have to integrate over K-per for the collinear distributions. Okay, so in light from quantization, since becomes, you don't have a time-dependent correlation anymore. In fact, the correlator becomes equal time correlator. The time except it's not real time, it's a fake time. And so therefore, you have this simple interpretation. And then the tricky thing is that what is the state of the proton? So the allegation is that you can write that as in terms of bunch of Fock states expansion and all the partons acting in a vacuum with the amplitudes. And then you have an infinite number of the such amplitudes. So this is called the light front wave functions. And you can solve this light front wave function by looking at the Hamiltonian equation. The light front Hamiltonian act on this, give you the mass squared 2p plus p. So this is, you substitute in here, just like a Schrodinger equation. And the H minus is called the light front Hamiltonian. Okay. And so you have this light front Hamiltonian, and you can solve this. You can get the wave function. You substitute in here, you calculate the Parton distributions. So that's the dream. Okay. That's a dream was on since later 1980s. Okay. When I was a postdoc. Okay. However, that for QCD, nobody has made it work. Okay. Not even a simple even an approximate calculation. Okay. And in 30 years. And in fact, I worked on this because Ken Wilson was urging people to follow in this direction. And so I worked on that in around 1994, 1995, and even write a review article, a small review article about light from quantization. And I quickly realized this is a dead road. And so I have not tried this for 25 years. And I found this is not gonna really, but people have done a lot of phenomenology. I mean, people have cooked up the light from Hamiltonian and diagonalize using a computer and then get some wave function. They're doing what's called a light from quark models. Light from quark model. I'm fine with that light from quark models. It's okay. It's inspiring, it's phenomenology. However, it's not solving QCD. Okay, so you can't solve QCD using this approach. Okay. Okay, so let me ask if you got any questions at this moment.
Can you hear me?
You probably need to complete your action.
Okay, can you hear me? It is, okay. My question is more like a request for repetition, if it's possible, because when you were doing the light from quantization, I didn't understood what you wrote in the anti-commutator relation. Again, I don't understand what's
The commutator relation.
yeah.
Okay.
Like I don't understand the writing, so maybe you can, if you could explain it again, that would be very helpful. Thank you.
Okay. So when you do the quantization of the fields, basically you look at the fields and then it's momentum conjugate. You postulate a commutation relation. And then you postulate this commutation relation usually when the equal time. Okay, so equal time. It means that the psi is at certain x, but at time t, the pi is a position some called y and t, but equal t. And then you postulate a commutation relation, which is something like delta 3, x minus y. So therefore, the commutes, if x is not equal to y, but it will have a delta function infinity when x is equal to y. So it's a momentum and its conjugate doesn't commute. Okay. Now, this idea can be used for a new coordinates, which is psi x. So unfortunately, this x is not the Feynman x. Okay, so you have some coordinates. Usually I use c mu. So therefore mu equal to 0, 1, 2, 3. So you have c plus minus equal to c 0 plus minus c3 divided by square root of 2. So now you have a new Lycombe coordinates. So now you have a fields, instead of postulated the equal time commutator, now you have the equal c plus commutator. So therefore it means that you're going to have, let's call it x again. Then you have a c plus, and then you have another one, the momentum fields with a y, and then you have a c, same c plus. Now you're going to postulate a commutation relation and x and y. And so this is called a light-front quantization. So the two fields are, the commutation relation is postulated when they are actually lying on the Lycombe here, okay, on this plane, if you like, okay. So this is called the initial data plane, okay, the initial data plane. And so that's how do you do the light-front quantization. Okay, I hope that answers your question.
So why is there an epsilon rather than a delta function?
It's a very good question. It has to do with the fact that you have to take the time derivative in order to get the momentum. So if you take the time derivative with respect to the epsilon, you get a delta function, I think. Okay, so that's this is one of the idiosyncrasy with the light-front quantization. People studied quite a bit of this thing in the early 1970s, but mostly in perturbation theory. And as I said, you can consider this theory as p is equal to infinity without using any UV cutoffs, without UV cutoffs.
Luke has a question.
I was wondering, are we able to relate the effective field theories to the Parton distributions via power correction? Or yeah, power expansion?
Maybe you can explain a little more your question. Which effective theory you're talking about?
So either the HQET, or I guess in relationship to this large momentum effective theory, and then match the coefficients.
I haven't gone to that yet. That was my next topic of discussion.
Okay.
Yeah.
I have a follow-up question to that, but I guess I'll save it.
Well, I can certainly start with this, and so let me start with huh?
More question before you go on?
Yeah, actually, I have a question. Like, can I think of the residual momentum symmetry that you can pick arbitrary finite residual momentum as a reason the infinite momentum boost preserves the IR properties?
That actually is just two different things. The infinite momentum boost preserve IR property, something which is different from the fact let me try to think. The residual momentum symmetry basically is the infinity plus a constant is still infinite, right?
Right.
If it's so, if you have a well-defined limit, then you should have that symmetry. Okay. So I think that, yes, you can think that residual symmetry now, where you boost things that, nothing changes anymore, and certainly infrared doesn't change either. And UV doesn't change either, right? It's a symmetry.
Right.
It's a strict symmetry now.
Yeah, I
With no approximation.
Mhm.
Okay. Okay.
So I was wondering about light front quantization. So naively, when you change your quantization scheme, you are going to wind up with a completely different theory. So how does one, when one goes from basically quantization via equal time commutators to this light from front quantization scheme, how do you guarantee that you're not going to end up with a theory that's inequivalent to QCD?
Well, at first you don't know. You at first you might say, hey, I have a dynamic system, I impose different kind of initial conditions, and do I get the same kind of evolution, right? However, that in a way, Lorentz symmetry guarantees you this, because as I said, you can think of light front quantization as the limit of p is equal to infinity. And so therefore you're basically making an infinite boost. And so you have to trust that the Lorentz symmetry is a really good symmetry, even you have to do the infinite boost.
Okay, thank you.
So you're doing a little bit more, actually. Of course, there's a subtlety between the limits. And so, yeah, the limited thing is a little bit of a tricky, right? Even though you're assuming everything, I don't know whether in the middle school, when you learn the open sets and close the set, you say, well, when you can have a set and the limit of it doesn't belong to this set, right? You can have that kind of situation.
Hi, Xiangdong. Also on this question. So even with boost, I mean, when you try to boost the correlator from equal time to get very close to the light cone, I mean, eventually the boost doesn't take you across the light cone, right? So how do we know that the theory on the light cone boost from equal time, boost from real time will eventually give you the same results? I guess this is something related to the previous question.
Yeah. This limit is a little bit of tricky here. Fortunately, in a Parton distribution case, that I think we can show that, as I showed you before, that these two are the same. That is, in fact, I think maybe you wait a little bit of that. What I'm going to talk about next maybe has a lot to do with that. In fact, is try to connect the infinite, the effective theory with the boost, and so therefore you can see the connection there. Okay.
Dong, is this a natural breaking point in your lectures?
Sure. If you like to have a break, I'm fine.
Oh, yeah, we do have the coffee here, so if it's a natural breaking time, I was wondering maybe we just take the break now.
No problem. And so we're gonna start in a half hour, right?
Yeah. So you have about an hour and a half more material to go through?
Yeah, roughly.
Okay. Then yeah, let's break for half an hour and then.
Okay. Well, I'm gonna have some drink here. Well, maybe some coffee, whatever. I'm around. If some people have questions, I can still, keep discussing.
We'll leave the Zoom meeting open and people can come up here and talk to you if they want.
Yeah, let me get some hot water and back in 5 minutes. And so, yeah.
Sounds good. Well, thank you for your first lecture.
Okay, no problem.
Light front quantized lectures. I did.
Yes. Yeah.
Where's Thomas? Yeah. Yeah.
Hey, Xiangdong.
Hi.
It's Gabe.
Hi, Gabe. How are you?
I'm good. How are you?
You're in Ohio?
Yes, I'm still in Ohio. I wasn't able to go in person.
Oh, okay, great. Yeah. So I'm excited to see you're gonna join us soon.
Yeah, me too. Me too. I'm really excited.
Great. So you're gonna have, yeah.
I actually had a question about the light front quantization stuff.
Mm-hmm.
So there's you're saying that the light front quantization is sort of it basically puts you into an effective theory by taking this infinite boost.
You're asking a great question. Let me try to answer this question very carefully, and I will repeat that during my next lecture.
Okay.
The light front quantization is so singular that we don't know how to define it at all loop levels. You can do tree calculations. I mean, you guys have been doing a lot of tree calculation, which is fine. I don't have any problem with that. The only problem I have is when you go to loop calculations, the light cone theory is so singular that it's very difficult to come up with a way that allows to tame all kinds of divergences. So that's first statement I want to make. Okay. The second statement I make may be that the only way you can define the light front quantization theory correct in a well-defined manner is to take that as an effective theory of a infinite boost. That is, you switch the order of renormalizations and the large momentum limit, and you got the theory that you at your hand is as good as any light front quantization theory, and that's the theory that is well defined.
Okay,
so I can only think of a light cone physics in terms of large momentum limit.
I mean, so there's like this recent work by Brodsky and some others, Mannheim and Loudon, that they actually argue that it's unitarily equivalent to instant time quantization.
Well, that statement is not very useful unless you know how to regulate the theory, because we know quantum field theory have divergences.
Mm-hmm.
Unless you know how to regulate the divergences in the both theories in a way that they show they're consistent. And in fact, there is no way that I know the light front quantization theory you can regulate all the divergences in a consistent manner.
Mm.
That's the problem. So you don't even know how to define the theory without having all the regulator in place.
Yeah, I mean, can you somehow trace that to the fact that it's an infinite boost? Because in principle, you're just doing a Lorentz transformation, and your theory should be invariant under that transformation.
Right. So you're on the two sides of the fence. One side of the fence says you're going to do the boost with the cutoff much bigger than the momentum you have. Then that theory is well defined. On the other hand, if you boost much bigger than UV cutoff, then that's the theory you don't know. And so then you try to define the ladder theory in terms of the matching. And then this is well defined. But otherwise, we don't know how to define what does it mean by boost theory, right?
Yeah.
So,
I mean, can you get around that somehow with, so like QCD is asymptotically free, If you
Yes,
could
you can
somehow
get-
take your UV
that's-
cutoff to infinity first, can you?
That's
fix
precisely the point. Whether the cutoff go to you can switch cutoff. That's the effect is the perturbative. You can calculate perturbation theory.
Yeah.
Yeah. So you can only define with that kind of matching. And what does it mean by light-fine quantization theory?
Okay.
So you build a bridge basically using perturbation theory.
Okay.
Yeah. So that's my view. I mean, this view is has been very fruitful, but I think maybe there are other ways people can do that. But so far, that's the only way I found that. How do you define a light-fine quantization theory?
Okay. Okay, that makes sense.
Yeah. So
Thank you.
so light-fine quantization is an effective theory of a theory with large momentums, and they just connect them. You can think of the large momentum is the effective theory for partons, or partons the effective theory for large momentum. They're mutually effective.
So I guess if you had like a conformal theory, would none of this matter? Because then you could
well,
just do the
will be-
boost, whatever.
Yeah, well, the problem is that this only works in asymptotically free theories. So if the conformal theory, I mean, obviously that we know that the UV fixed point in QCD is a conformal theory, okay? But it has to be a trivial theory. So if it's not a trivial theory, then you don't need, in other words, the UV has to be a free theory.
Yeah.
In fact, we don't even know how to define a quantum field theory if a UV is not a fixed, is not a free theory. Because we don't know how to calculate the UV properties. And nobody knows how to calculate the UVs using non-perturbative methods, which doesn't exist.
Yeah. Okay.
Yeah. So strictly speaking, we only know how to define a quantum field theory, which is asymptotically free. And if it's not, then there has to be a cutoff theory, like QED. QED is a cutoff theory.
Just putting like an explicit UV cutoff.
You don't have to, because what happens, the cutoff is on the Landau pole basically, and so the scale is terribly big. So you don't need to, the problem doesn't show up until high order in perturbation theory, and so it's for practical purposes it's moot, but it's not a well-defined quantum field theory.
Okay. Okay, I think that answers my question pretty well.
Okay.
Thank you.
No problem. No problem. Maybe you should get some coffee too.
Yeah, I'm gonna actually try to go have dinner quickly before your next lecture starts.
Okay, good.
Phil, do you watch lacrosse at all?
Lacrosse?
Yeah,
Why? No,
because UVA has a really good lacrosse team.
not watch. I just know we do trash at basketball
Okay,
and football.
I just figured out you're East Coast and UVA. I went to Dick's Sporting Goods looking for a lacrosse stick. I was like, "Hey, lacrosse stick set?" And they were like, "The what?" And you just can't find them in the.
Where I went to grad school, Caltech, the basketball team was so bad. Like one game, they actually lost by only 1 point. This was so remarkable. They made a movie about it. The whole movie about how Caltech did well enough to only lose the game by 1 point. Called Quantum Hoops. It was a real movie.
Quantum what?
Quantum Hoops. I think MIT blowing out Caltech by like 50 points shows up in that movie.
Hello.
We can start in a minute.
Okay.
Patrol the hallway. Let's see who's there.
Okay.
Okay, reminder to in-person participants, if you haven't signed up for dinner, go into the Slack site and find the post in the hotel channel. And if you're coming to dinner, click the taco. Or the avocados, you can also click, you have the unicorn. You can click one of the other icons as well, or your own food item. Again, the dinner starts at, it's a 7 o'clock Tomasitas, which is about a 10-minute walk south, whichever way south is. That way. And they have a bar, you can go earlier if you want. But there are reservations at 7. And tomorrow, of course, yeah, we only have the morning session, and you've probably already done this, but make sure the hotel knows when you're actually checking out, whether it's tomorrow or the following day or another day.
By what time do people need to check out if they're checking out
I
tomorrow?
remember what checkout time is. 11. It's not a hard cutoff. It's more of a dimensional regularization. Yeah.
They're really big engagement rates here.
Okay, I think, yeah, Xiangdong, why don't you go ahead and begin the rest of your lectures.
Okay, well, I hope you had a good break. And during the last an hour and a half, I was trying to impress you with a new way of looking at partons. And in fact, it's not a new way, the oldest way to look at partons, the Feynman's parton. And you can write down a formula in field theory, embody the Feynman's idea. That is, you have infinite momentum states and calculate the correlation functions in that infinite momentum states, and Fourier transform, you get a parton distribution. And the great thing about this formula is that these space correlations. So remember that these correlation functions are along the z direction, and so there's no time in there. Okay. And so this is very beautiful, right? It has no time dependence. And however, this formula is completely useless for 2 reasons. Reason number one, nobody knows how to calculate a Hadron wave states with infinite momentum, right? And if you know a method, let me know. Nobody knows how to do that. And second is that this calculation is done before the UV cutoff is the momentum, infinite momentum is taken before the UV cutoff is imposed. And this is in fact not what we do quantum field theory. In quantum field theory, the first thing we do is to impose a UV cutoff, right? And so therefore there's these two problems. And however, that these two problems can be solved in the following way. First of all, we don't have to work with the infinite momentum. We can work a very large momentum. And remember the expansion, that is, if you look at the difference between large and infinite momentum, the difference should be go in power of m times p, m over p to the some power, okay? Let's say squared. And so therefore you can approximate the infinite momentum by a finite momentum, okay? And this, what we do all the time, right? And you know, the field theory is continuum, so therefore the degrees freedom, next to degrees freedom, the distance is 0. However, you put a lattice, so therefore degrees freedom have a finite, so the continuum become discrete. And so therefore that I can also approximate infinite momentum with a finite momentum. Why not? So long as they know how to control the approximation. The second problem is that suppose you want to do this on lattice and you want to calculate an equal time correlator in a large momentum state. You can only do this with a lattice cutoff much, much greater than PC, because otherwise you cannot approximate the states very well, right? And then the state's going to fall in between the cracks on lattice. And whereas the formula here says that you should take the PZ much, much greater than 1 over A. And so therefore these two different limits, however, we can try to, all of these involve the large momentums. And we know that for the large momentum, the QCD, there's this property of asymptotic freedom. And so therefore the difference here is should be perturbative. And so therefore we should be able to calculate what are the differences in taking these two different limits. And so we need to calculate the difference. And difference is perturbatively calculable. This is called a matching coefficient. So we do that all the time in effective field theory. We calculate matchings between, you know, different limits. And so therefore, because of that, you can write down a momentum density as a function of momentum PZ, large momentum PZ, can be matched to a Lycombe distribution with momentum fraction X renormalization scale mu with the following matching formula, with the C, which is a Y divided by X and PZ divided by mu. And you can see that this is now the Lycombe distribution, that what we want. And this is what you can calculate on lattice. And the limit is taking, and in fact, I should put a lattice spacing dependence on A, and so therefore this is A dependence in here as well. And this is the perturbation series. It can be calculated 1 plus alpha S alpha squared, etc., to high orders. Okay. And then, of course, that you need to take into account the power corrections and 1 over PZ m to the square plus some other stuff, which you need to take care. Okay, so therefore you arrive at a formula, which I call the matching formula. I'm not going to call it a factorization formula. Some people like call it a factorization formula, but this is really a matching of infrared physics. And so the infrared physics of Lycombe distribution should be the same as the large momentum distribution. And this thing can be simulated on the lattice. So if you do this and a large enough PZ, then you calculate a high order, enough high order perturbation theory, so you may have a hope to extract Parton distributions. And so this is called large momentum effective theory, okay? Large momentum effective theory. So basically, now what is so effective? And there's 2 points here. That is, you have a finite P, you have a theory which is a full QCD. And now when P go to infinity, you got partons. That's an effective theory. So parton can be considered as effective theory of this theory, P go to infinity, but you can also consider this theory as a defective theory for partons, because parton at a P goes to infinity, you don't know how to solve, and so therefore you construct a theory that gradually, you know, systematically you can solve this. So therefore, they're mutually effective theories. All right, so this was proposed in 2013 to 2014, okay? And we give it a name called LaMET, large momentum effective theory. And there's many things I can say about LaMET, because the limitation of time, I'm not going to be able to, you know, give you a lot of detail, but let me give you one example. Okay, an example. It's a lot of calculations. I think maybe there are 100 papers written on this, many hundred. Okay, so maybe 200 or 300 papers on this subject. And so what you do is first you're calculating in a momentum, large momentum states, you can calculate the momentum distribution. Okay, you can calculate the momentum distribution. In fact, you calculate a correlation function. There's a function of z, pz, and a. Okay, you calculate a correlation function, and then you renormalize this, because this is going to have a lattice dependence. It turns out that the Wilson line that you put in the middle of the operator will generate linear divergences. So this leads to linear divergence. And so therefore, you have to renormalize this. And we know how to do that. In fact, we know that this correlation function going to have the dependence on A goes like Z alpha S divided by A, and a perturbation series in alpha S, then times something finite, okay? And which you can take A go to zero limit. And so therefore, and let's say you can match to the MS bar scheme. And so you take care of the divergence. And then after this, you Fourier transform this to the momentum space. You need a Fourier transform, and this becomes lambda y, d lambda, and f of this is lambda pz, and lambda again is zpz. And then you got called a quasi PDF. Okay, this is called a quasi PDF. It's not PDF yet. Got a quasi PDF. And then finally, you match the quasi PDF to the real PDF with a matching coefficient. Okay, x mu, and then you have a mu. This is the MS bar, and this is also MS bar. And this is a y divided by x, and mu, and pz divided by mu. And so, and then of course, you also high order corrections, etc., as you have to take care of. So this is the program that I outlined basically in 2013, that how you do the calculation of partons using lattice. Okay, so now let me show you that one of the most recent calculations that done by a group of people from Brookhaven National Lab and also Argonne National Lab, called lattice determination of x dependence of PDF, next leading order. Okay, so that done a calculation with very small lattice spacing, a equal to 0.04 Fermi, 0.06, and with pion mass about 300 MeV, boost momentum as large as 2.42 GeV. And so first thing you do, you calculate the special correlation functions. So this is lambda equal to ZPZ. You calculate a correlator as a function of PZ. And you can see that PZ very small, it decays very quickly. And when PZ gets bigger, the correlation gets longer, and then gets bigger, it gets longer, and you see that large momentum will give you very long range correlation. In fact, when the PZ go to infinity, this correlation become, this is an exponential decay here. But when PZ go to infinity, this decay is not exponential anymore. It's algebraic. In fact, goes like lambda to some algebraic power. And so this will contribute the small x properties. Okay, if you Fourier transform to small x and goes like to some power of x, and so you Fourier transform this, you got this exponent. But in reality, first, I cannot really calculate. Oh, so let me try to make another very important point I forgot to mention. You can see that the corrections I mentioned to you, there are corrections on the order of PZ squared. And if you do a careful analysis, you find that the correction goes like 1 over x PZ squared, or 1 over 1 minus x squared, x PZ squared, okay? And I'm not gonna explain to you why. You can read our papers. So therefore that this expansion parameter, as PZ gets large, is only effective when x is not close to 0 or 1. If the x is close to 0, 1, then this expansion parameter is not very small, so therefore your calculation is not going to be very good. And so therefore you should stay away from the endpoint region. Okay, so, but in any case, that the fact that you cannot calculate a very long range correlation with a finite p, it means you cannot really calculate a very, very small x, okay? Otherwise that, you know, people doing small x will be out of business, okay? And so fortunately, we're not gonna able to, or fortunately, unfortunately, we're not gonna solve their small x problem with this approach. Okay, so you take the largest momentum possible, and then you Fourier transform into, you do the renormalization, as I said, subtract away linear divergence, and match onto the MS bar scheme. And what you're gonna get is this called a quasi-PDF, which is this gray band here. And then you remember that you have these corrections of the matching. So therefore you plus next leading order, which is the order of alpha. And people calculate to alpha squared, so it's the next leading order. So when you do all that, then you will get a green band, green curve, which is next leading order, okay? Good. And so now you also look at the momentum dependence, and you can see that the different momentum of hadrons, you can do the same thing. And eventually you can see that the largest momentum is this blue curve. And the next smallest momentum is the red curve, which is below the, you can see that at the quasi-PDF level, different momentum, they're all very different, scattered all over the place. However, when you go to match to the PDF, you can see that as the momentum gets bigger and bigger, they really converge in this blue curve, okay? So now you can compare with experiment. And as I said, you can't really calculate when x very small and x very large, so you basically threw that out. And then you do all the calculations, you found that the red band is the prediction of the lattice calculations. And the experimental fits to the pion PDF is shown here as the black curve. So you can see the black curve here. It's almost on top of this, all right? And this is like magic, you know, and this is, the red thing is completely the QCD prediction without any, you know, kind of wiggling space, except the fact that pi is not still, you know, 140 MeV, but maybe it's not so important here. And the green is some other method to analyze the same data using so-called pseudo PDF, which is proposed after the LaMET theory. You can see that this method actually is not yielding a good answer. So therefore pseudo PDF actually is a bad idea, okay? So, you know, you shouldn't do pseudo PDF. There's no reason to do this. And so in any case that you can see that there's a good agreement between the red band and experimental data, but experimental data also have some uncertainty. So next challenge is look at the nucleon. So I'm not going to talk about this. We're working on this. There's a lot of calculation on nucleon. We still haven't brought everything under control, but the hope is that eventually we will reproduce the experimental results. And so this is basically a calibration of the method, you know, and to show that this idea actually works. Well, I think that in the next, you know, few years, 5 to 10 years, people will, I think in most cases will provide curves more accurate than the experimental data can provide. Okay, certainly in a pion case, I think that even there room to improve that, make it a very small error. I think in certain places is 5% in terms of PDFs. Okay, so this is all I want to say about, you know, a very quick quick introduction to the large momentum effective theory.
Xiangdong,
Yes.
I have a question again because I was not paying attention.
Okay.
If you said it, could you repeat what the limitations are at small x and large x, and what determines the range of validity in
Okay,
X?
so let me actually, I have a lot of time, so therefore I can answer your question more slowly. So if you have a hadron with momentum pz, then splits into two parts, with the parton with the xpz, and with the remnants as 1 minus xpz. Okay, and so in doing the dimensional analysis, that our expansion parameter is some lambda QCD divided by a larger scale, which could be PZ, could be XPZ, could be 1 minus XPZ, because they're all large. If they're not large, you cannot view them as a partons. And so therefore it could be XPZ squared. It could be lambda QCD divided by 1 minus XPZ squared, because this is a worst case scenario, which you have to take into account. And so even though you have a very large PZ, let's say 3 GeV, okay? But when x equal to 0.1, and this now becomes 0.3 GeV. So therefore, all of a sudden, this expansion parameter is not good anymore. And when x is very close to 1, then this scale has become small, so therefore this is not a good expansion parameter. And so the expansion parameter becomes bad when you're close to the endpoint region. So that's why we cannot really calculate the small x and large x region. Does that make sense to you?
Yeah, so all the constituents of the proton have to have large momentum.
It's what else could be argument, right?
Yeah.
In other words, there's no reason that it shouldn't appear in the denominator. They're all supposed to be large, right? In a picture of partons that you have to, you know, when x is too small, then it's a soft parton. It's not a, you know, it's not a collinear parton anymore, right? It has to be a collinear modes. And when x is too small, it's not a collinear mode. It's a soft mode.
Can I ask a question?
Yes.
So go back to the slide with the pion distribution.
Yes.
Or you answered Chris's question. Okay, so PC is 2.5 GeV.
Yes.
And X, let's take X to be a half. I mean, it's then X times PZ or 1 minus X PZ is like barely over a GeV. And
right.
The power reflections are supposed to be lambda QCD over that GeV. Does it surprise you that this works as well as it does?
It does surprise me a little bit.
Power correction.
It does surprises me a little bit. It works as well as what's shown here. Okay.
Mm-hmm.
Actually, it actually works as expected for large X, because the large X does have problems. And you can see if in this insert plot, when the X is very large, you can see the red curves is not going to even go to 1, and obviously go to 0 as it should be, because you're gonna get the expansion just break down. And so therefore, for the large X, I even say 0.8 is a little bit too radical. Maybe it doesn't work already to 0.7, right? Or 0.6 even, okay? So for large X, it's not working very well, okay? But, huh?
But that was expected.
That was expected, exactly. Now, for small X, why it can work as well as it has been? There is let me tell you that there is a renormalon calculation by other people, which could show that it's a square root of X appears in there, which could be the reason, but I don't know, okay? So it appears, but then those are just simply, dimensional arguments, right? So, the actual thing is dynamical, okay?
Yeah,
So we don't know what kind of dynamics actually is controlling this. It's simply a guidance. It by no means it has to be that way. Does that answer your question?
yeah, I guess, but I mean, no, I guess it doesn't really, because I'd say that if for X equals 0.8, your 1 minus XPZ is like 400 MeV.
Yeah,
You're spot on, and it's like, I mean, it's great. It seems like you got lucky almost, or maybe you have to rethink harder about what the errors really are. I mean, it's a good
well, the only thing you can answer this question is calculate the next order, right?
Yeah.
So that we in fact work out the formula to show how to calculate the next order, and then to look at the correction, how big are they, right? So without calculating next order, I simply don't have a good explanation why it works as well as shown here.
Is this typical, the accuracy of the agreement? I mean, you should have.
Yes, it is quite typical. It is quite typical. We see this, we always struggling with large X because large X doesn't seem to work so well, but it works remarkably well at smaller X. It has no right to work that well, but I don't know why.
Yeah, that was my impression reading that chapter of the handbook. It's like, we're in this large PZ limit, and yet you guys are getting great results, which is good.
Yeah. Yeah, I have no read. I had, it actually baffles me. In fact, I was very pessimistic for small X. So when I talked to Raju, I said, I can never think about in my life that can calculate 10 to minus 3. Okay. But I don't know. I mean, here, we're talking about, also 0.05 already. It works pretty well. Maybe if you jack up to the 10 GeV and maybe all of a sudden you can do very small. I simply don't know. It's kind of a.
Maybe I can add a couple of comments.
Yeah.
So first, at small x, the relative size of the arrow is seems to be under control. Maybe still like 10% or so. But if you look at the absolute size of the arrow band, it blows up when x becomes smaller. It's just because that the central value of the PDF also blows up. So just
but you don't have any data there either. I think that ion data doesn't really. So all of these are very small excesses. Both experiment and theory are fictions. So don't take that as a agreement.
Yeah. And my second comment is about the logarithms of the large logarithms of mu over xpz. So the actual logarithm is mu over 2xpz, as you can, as I can show you by Fourier transforming the logarithm of z square mu square from the position space. They correspond to each other, although in practice they are not equivalent when you add a finite PZ. So when you have that extra factor of 2, that gives you a little bit more window for the perturbation theory to work. And we have also estimated the size of the theory uncertainty by varying the factorization scale mu by a factor of square root of 2. And what we see is that the uncertainty from the variation of the mu is not significant. It may amount to a few % variation of the central values. So somehow this convolution of this matching coefficient with the PDF is not very, for the middle range of x, is not very sensitive to the logarithms. The majority of the correction comes from the finite part of the matching.
What is the theoretical uncertainty here? I mean, clearly it doesn't include your power corrections. How did you?
The theory, so the red band, the dark red band is the statistical uncertainty. Okay. And there's a lighter red band is the scale variation. So we change the scale mu, which is 2 GeV by a factor of square root of 2. And then we get the final PDF at a different mu, and we evolve the final PDF to 2 GeV. And then that would become our theory uncertainty. But we haven't estimated the power correction uncertainty because we don't, our data have different statistical uncertainties at different momenta. At smaller momenta, the data has much smaller statistical uncertainties. So if you do a naive infinite momentum extrapolation, then this extrapolation is mostly dominated by the smaller momentum data, which is biased because it could have larger power divergence, power corrections. So eventually we just use the largest momentum result as our final prediction. We haven't put the estimate of the power correction uncertainty in this plot here.
That would be huge compared to what's there.
Yeah, it's about, we did a very naive estimate. It's about 10% at 0.8. 10% power correction. That's we did a naive infinite momentum extrapolation, and in that naive extrapolation, the power correction is about 10%.
That's not for PZ equals 2.5 GeV. It's extrapolate, right?
Yeah. Yeah.
QCD is full of miraculous expansions that work way better than they should. In our QCD for charmonium.
Yeah, that's what we're doing.
Large MC.
Are you guys cool now?
Any other questions while we have the lecturer paused? Philip has a question.
This is the follow-up question that I asked earlier. But once you have this relationship between the effective field theories and your PDFs, the matching coefficients, is it straightforward to then construct the DVDs, or are there initial steps that we need to take into consideration?
Somehow the voice a little cracked. I didn't. Can somebody repeat the question?
Here, the questioner will repeat the question.
Okay.
This is a follow-up question. But once you have the relationship between the effective field theory and the PDF via the matching coefficients, is it straightforward to then construct a GPD, or are there other steps that we need to take into consideration?
For GPDs, it's the same, exactly the same game, except that the matching coefficient can be a little more complicated because you now have the C dependence as well. So everything will be the same game. Okay. Does that answer your question?
Yeah, thank you.
Okay, everything will be the same. So if no more questions, I have an hour. I can finally reach my main topic of the discussion is about the TMDs. Okay, the TMDs. Okay, so what is a TMD? Well, a TMD, if you do the lifelong quantization or using the lifelong quantization and whatever, it means that you don't integrate. You're not going to integrate out the K-perp. period. That's it. So you're gonna keep the K-perp dependence. And you can still formulate it in term, well, so before I talk about the formulation on lattice, I'm gonna use the standard formulation. I'm sure that Ying has spent a lot of time to explain to you in gory detail what a TMD definition is, okay? So I'm gonna take a very simplistic approach. That is, these unsubtracted TMDs will be XK-perp, and then you have a light cone correlators, minus lambda n over 2 and minus B perp over 2. And then now you have a W, and then you have a psi lambda n over 2 and B perp over 2. And then you have a state, you Fourier transform with respect to the B perp and lambda. And so here the Wilson line is going to be a little complicated. And this now is going to direction n, the light cone direction. And this is going to be B perp space. And so you have the fields living in this 2-point psi bar. And then they're all going along the light cone direction going to infinity. Okay, so this is strictly along the light cone direction, going to infinity. And then, of course, that if you choose the A plus equal to 0 gauge, this light cone link goes away. However, there's still a light cone gauge link at infinity, which connects these two, which does not disappear, okay? So if you choose light cone gauge, you would have to have this gauge link at infinity to make things work. And this, in fact, is the 0 mode, okay? So this is called corresponding to 0 mode, or people in the soft collinear effective theory, this is really the soft gluon, okay? The soft gluon, okay? The soft gluon. And so you need this soft gluon to make this into work. So as you can see that then the TMDs is inextricably connected to the soft gluons. And you will see that in fact, this guy, as it defined here, has the light cone divergence associated with this gauge link going to infinity and on the light cone. And those are the soft gluon divergence, okay, which are called a soft gluon divergence, or light bound quantization is called a really 0 modes problem. Okay, it's a 0 mode problem. And so therefore you have to subtract, or you must regularize this 0 mode, or renormalize the 0 mode. The way to renormalize the 0 mode, you define a soft function, which is the SB perp, and then you have bunch of Wilson lines here. You got the W along the P direction, B perp, W along the N direction, B perp, and then you have the W0 and WP and dagger 0. So the physics of this soft function basically correspond to a cross section that when you have two light cone line P and N, they each radiate soft gluons. Okay, those are color charges radiate soft gluon. You calculate the cross section of this, you square this. So it's basically it's a soft gluon radiation cross sections. And that, of course, is dependent on the 0 modes. And because none of these gluons are going to carry a substantial amount of longitudinal momentum. And so therefore you can do a subtracted version of PDF, which is going to be X B perp. When you subtract, you introduce a rapidity divergence, let's call it zeta. And so therefore you can use this naive definition, which have light cone divergence, and subtract by square root of S. So therefore now this gonna have the rapidity regulator zeta in there. Okay, so and then this zeta dependence obeys the so-called Collins superequation, which you have heard many, many times, I'm sure, that goes like a Collins superconal K, which depend on the B perp, and B perp and which is a renormalization scale mu. And this guy, because the B perp can be any value, so therefore, when B perp is large, this is non-perturbative. Okay, non-perturbative. So this is a very different from the standard renormalization group equation. There you have, I think I need to have a logging here because otherwise I should have the F in the right-hand side. This is different from standard renormalization group equation because there the right-hand side is always perturbably calculable to order perturbation theory. And this thing is not perturbably calculable in order perturbation theory unless B perp is very small. In this case, you can do perturbative calculations. So this is a lightened review of about the TMD physics, TMD definitions. And so I will take this as my target infrared physics to match. Okay, so what I calculate on lattice, I have to match onto this definition here. Okay. And so therefore that first thing I do is I define a unsubtracted lattice version, unsubtracted lattice TMDs, okay? And I first did this in my 2013 paper. And basically I say, well, instead of N, now you consider as a Z direction, and this is the B perp. And then you have two quark fields, and this is now going to infinity along the Z direction. And then this is also along the Z direction. And if you like it, you can complete it by a staple, okay? And so therefore, this will be a unsubtracted TMD. Okay, so I'm going to define a unsubtracted TMD and quasi, I use a tilde, then X B perp. And now this guy going to depend on PZ because I have the external state with a momentum PZ, and I have the two psi and with a W, and this is PZ. And then this kind of a B perp dependence. And then the longitudinal separation is going to Fourier transform into a variable X. And that's it. So this is like a no-brainer. After I, spend an hour and a half explain to you how the LaMET works, and it's just an easy construction, right? You construct something which is calculable on lattice, okay? And in a paper in 2015, and Feynman and myself studied this object, and we basically show at one loop level this quasi TMD, if you call it, and in fact it should be called quasi TMD, it's because it's still unsubtracted. They have a PZ dependence here, and we basically in one loop calculation and found that this PZ dependence in fact obeys a, remember this is like a booster renormalization group equation I mentioned to you before. So as the PZ boosts changes, and we discovered that this guy obeys a column super evolution equation, which is K depend on B perp and G depend on mu. There's additional thing which is called a G, and then F0 X B perp and PZ. Okay, so this PZ dependence here is completely, in a certain sense, kind of related to this quasi definition. But the good thing is that this dependence PZ obeys this equation, which, by the way, we only show this to one loop. And then we postulate this works to order perturbation theory. So, this is the Collins superkernel, which I discussed earlier in the Lycon case. But this piece, the G, is perturbably calculable. Okay, it's calculated in perturbation theory, so you don't have to worry about that. And so this, we pointed out that is a way you can calculate the Collins superkernel. Okay, so Collins superkernel, you can calculate on lattice using this evolution equation. Okay, and so the MIT group and by Yung Chao and then Stewart and Shanahan, and they actually went ahead and did the calculation around 2019, 2020. So they wrote a bunch of papers on this and included numerical calculations and what is theoretical formalism to make that implement this. So now let me show you that probably you heard from Shanahan's talk about these calculations. So let me just show you that there has been actually quite a few calculations. These slides are taken from the LaMET 2021 and showing various kind of calculations. So first of all, as I said, that this kernel can be calculated in perturbation theory. So therefore, this is a 1 loop, 2 loops, and 3 loops. Okay, so as you can see that it quickly becomes divergent because alpha B perp becomes extremely large when the B perp becomes large. And so therefore, perturbation theory can work up to here. And then you have the calculation by very early days, as I said. I'm not sure it has the first result by oh yeah, Shanahan and this first Shanahan, Wagman and Zhao at 21. It's this curve by MIT groups. And then there is the ETMC calculations by Pink. And then there's recent calculations using 1 loop matching. This is the red one, the red. The risk it actually hasn't appeared as a preprint yet, but it will come out pretty soon. I think this is the 1 loop matching calculations, and compare an earlier calculation by LPC with the green one, with a larger error bar and slightly different from this red points. So therefore, you can see that people really have capitalized on this. Oh, okay, the reference is the right-hand side. I can see this. Okay, so 1 loop calculations by Shanahan et al. And then also Schremer. And so this 1 loop, this is tree level, and then this red ones are new, unpublished. Okay, and then you can see that quite I would say fruitful in calculating the Collins super evolution kernel using lattice. Okay, so that's kind of very nice development. And so now let me press on, try to complete the definition of the F-tutor on lattice. Okay, now the next problem I'm going to take care of is so-called the pinch-pull singularities. Pinch-pull singularities. Now, what are they? Well, you can see this Wilson line going to go up to infinity in parallel. And so what they do? Well, they're going to exchange a lot of soft gluons. They're going to exchange a lot of gluons in here. And when they're exchanging gluons, and they're going to very look like, LC, if you use the LC reduction, they're going to generate a something which is very much like a heavy two quark, anti-quark bond states. Well, not, with a fixed distance B perp, right? And so you put 2 quarks, 2 sources, and 3 bar, and with a fixed distance B perp, and let it evolve for a long time, it settles into a ground state, all right? And so therefore, that this Wilson line will generate a potential, basically. And so therefore, this, you have to subtract away because this, and what happens in Lycombe case, all of this is equal to 0 because here, just a second, this is Lycombe n, and all of the Wilson line, you have interactions of proportion n mu and nu, So all of the n's and n square, so therefore none of this like cone going to contribute. So therefore on lattice, you have to subtract this pinch pull away. So how do you do this? Well, it's very simple. In fact, you can just divide the, let me see what I have in there. You can divide the f of 0, which is defined upstairs, by square root of Wilson loop. Okay, because the Wilson loop is way to calculate for you the potential. And if you divide by the Wilson loop and then you subtract away the pinch pull, okay, and not only that, you also do very nice things for linear divergence. Remember that all of this Wilson line have linear divergences. They're very bad stuff for your lattice calculations. And you can choose this Wilson loop has the length of the Wilson line the same as the one which you have in the W here. So therefore that, because the Wilson loop linear divergence is proportional to the length, and it goes like RFS divided by A is lattice spacing. And so therefore, if you choose the length to be the same, numerator and denominator, and they cancel. Okay, they cancel. So that's great. So not only that you take care of pinch pull singularity, you take care of linear divergence as well. And even better, you're taking care of the corner divergence. So what happens if you have a, let's go back here. If you have a gluons flying in around the corner here, they generate enormous dimensions. So you have two 90-degree corners. So therefore you want to cancel the singularities, log singularity come out of these corners. You can do it with Wilson loop because here you got 4 corners. You take a square root that effectively is 2 corners. So all the corner divergence goes away. Okay, so you got a corner divergence goes away. And so this is very nice. All right, so you take care of the pinch pull, you're taking care of the linear divergence, take care of the corner divergences. So this is the right combination for you to think about on lattice and match to the MS bar scheme. Okay. However, there is another problem. Okay, another problem. The problem is that, again, related to the fact that this guy has 0 mode. Okay, has 0 mode or soft mode divergences. And this 0 mode and soft mode divergences has to be canceled. And it has to be canceled similar to the light cone case. You have to cancel with 2 color sources. One is 3, another 3 bar, and it radiates lots of soft gluons. And you have to calculate this cross section. But in this case, you're not going to calculate it with these 2 Wilson lines in the z direction, because if you there's only one z direction, so therefore it cancels. So therefore these 2 lines has to be in the fact that one is in P, and remember the light cone, it has a 1 in P, another in N. So the question is, how do you calculate this? Okay. So this is, you have to cancel the soft divergences or rapidity. You need to regularize the rapidity. And this, I think, is the biggest problem with the TMDs. In fact, when I was working on this a few years ago, at one point I was very pessimistic because I cannot come up with a way on lattice. You can simulate 2 light cones at the same time, right? So in a PDF, I only have 1 light cone. And so therefore I can try to boost in one direction. Then the light cone can, becomes a special correlation. But when you have 2 light cone, how do you boost this? So this becomes what I think was the bottleneck, basically, for complete calculation of TMDs. This is the bottleneck. In 2019, 2018, got a brilliant postdoc, and 2 Lius, and Liu. And they work with me, and I threw out this problem to them, say, can you think of a way to calculate it on lattice for the softer factors? Is that possible? Because it's almost like impossible because you have two opposite light cones. How can you boost that into a Euclidean calculations? And well, it turns out it is possible to calculate this. Okay, so let me show you that how this can be done. So basically they come up with the following construction, okay? So let's say you have a pion. You have a pion moving with extremely high momentum in a p direction. Okay, p is a light cone. I mean, it's not exactly a light cone, it's an off light cone because pion has finite mass. But it's very closely hugging the light cone. So therefore the leading component is going to be a quark and anti-quark. And then imagine that you have a baseball bat. You have two baseball bats. You hit the quark and anti-quark and let it go the other direction and go to the n direction. Okay, so now a pion, instead of going the p direction, now is going the n direction, also flying very fast, close to the light cone. So this is the other light cone. And then these two baseball bat, they separated by b perp. Okay, they're separated by b perp. And so basically in the end of the day, now this thing is a form factor. It's a form factor, which you got a pion state in the p direction, another pion state in n direction. Then you have a transition current. Basically, you have a psi 1 at b perp with a gamma psi 1, psi 2 at b perp. Okay, this is a 1, this is 2, then 1 and 2. And then you hit one of the ones, and then you gotta, you know, this is the b and b perp away, and then you have another operator which is psi 2 and a 0, psi 1 a 0. So it's not a usual form factor, but it's a non-local form factor because, however, these two currents are fixed in space. And so you calculate the form factor, the function of b perp. Okay, so you got two Wilson line. You can see you got a, you know, two Wilson line in the different directions, and you can show that the softer factors that you want is just proportional to this form factor, and then times the wave functions of pions and with the b perp, another pion wave functions with the b perp. So all you need to do is you calculate two wave functions of pions, leading amplitudes, and then calculate the form factor. We know exactly what to do on lattice because they're time independent. And so you get the softer factor calculation. So I think this is the most important elements of the LaMET calculation for the TMDs. And so once you have the lattice subtracted quasi-PDF, and then you have divided by the softer factor, then you can match onto the light cone TMDs, okay? X, B, perp, and zeta, okay? And this matching, again, is entirely predictive, okay? So this is the calculable on lattice. This is the light cone target TMDs that which you want, and appears in the Jiaoyan factorization formula. And the difference here is a perturbation series in alpha S. In fact, there are some mismatch in rapidity because this guy has a rapidity here is actually PZ. And so therefore that you have a log of C and PZ, and then times the column super evolution kernel, which can appear in here, and then plus a perturbation series in alpha S, okay? That's it. So therefore you can, so this problem basically was solved in 2019 with two papers, which I quoted earlier in with and Liu and Liu, okay, Ji, Liu and Liu. So In first paper, we show how the soft factor can be calculated. And second paper, we show that how to use this soft factor to arrive at a factorization theorem and well, a matching formula, I should say, a matching formula between lattice quantity, calculable quantities, and the standard definition of Lycombe distribution, and with some perturbation theory. And so this is a solution for the TMD on lattice. So now let me show you that the people have already calculated these soft factors on lattice using the pion form factors, okay? And again, a function of B perp. And you can calculate, you can see that we have pions moving at 1 GeV, 1.5 GeV, 2.11 GeV. And so they're increasingly close, hugging the Lycombe. However, the error gets bigger as pion momentum gets bigger. Okay, so those are gamma factors of boost. And then they can see this is the one loop calculation in perturbation theory. And then people have done this again to 3 loops, or even, I don't know, maybe even higher. So you can put in all the perturbative but this is a completely non-perturbative calculation of the soft factor. And so armed with that, so the soft factor is calculated. And so next thing is to calculate the F tutor, the quasi PDF on lattice. And I know people are calculating this right now, and not a single paper has been published yet, but I know it definitely will have a paper this year in calculating F tutor. So if F tutor is calculated on lattice, and the perturbation theory here is already, I think, to 1 to 2 loops, and Collins superkernel has been calculated. And so therefore, eventually we'll arrive at a Lycombe TMD and from lattice, okay, in terms of X, B perp, and zeta, okay? And so once this appear, we can nicely compare with all the phenomenological fits, okay? I'm sure you've probably seen some of the phenomenological fits. It will be very nice to see that, whether this is gonna agree with the experiment or not, okay? So let me also, in all these discussions, let me also enumerate the contribution from the MIT group that is Stewart and Yongqiao. Besides the fact that they have calculated the first, they call it super evolution kernel, they also conjectured how to arrive at a factorization formula. And most recently, that they have a paper appeared that showing essentially the same factorization formula we got in 2019, however, with some new twists. That is, they also showed in lattice where you construct it using what Engelhardt is going to tell you tomorrow, that they can also find a factorization formula to that. And I must confess that I don't understand what Engelhardt these people are doing. I have studied hard enough and to show what they're doing, and then it actually entails a factorization formula. They also looked into the Lycombe correlations using what called it Jima-Yuan definitions, and also Collins definition, and show they're similar to the standard Lycombe definitions. And the difference is only a perturbative matching factors. But I think that in terms of the lattice factorizations, that this thing has already appeared in 2019. However, that this is not a ironclad proof, okay? And we don't have a ironclad proof. We have some reduced diagram discussions on this showing that's plausible. And the new paper by MIT and Yongqiao and other people, they don't have a strict proof either. It's an argument, I would say. And so we're working a long paper, almost 100-page paper, to prove this factorization actually works to order in perturbation theory, but it's quite an undertake. I hope to finish this in the spring. And so if you're really interested, that we're going to try to present a proof, which maybe not everybody will happy, but it will make a lot of people happy. So that's all I have. I think I still have 2 minutes, so you can still ask a question.
More than that.
Okay, well, it's the time for dinner then.
Question.
I'm first.
Yeah, yeah.
Sorry.
Can I see your full boxed formula there, the 2019 formula?
Yes.
Which, can I ask, how does the Collins-Soper scale zeta appear on the left-hand side? Like, what does it mean on the lattice?
And the lattice is related to PZ. So in fact, that the Collins-Soper whatever scale, the rapidity scale is related to PZ. Okay, so this is reasonable because what happened is that when you have a finite momentum for Hadron, you know the X has a natural cutoff. The X natural cutoff is lambda QCD or Hadron mass divided by PC. And so therefore that this is kind of rapidity cutoff for the left-hand side. The right-hand side is C. And so therefore, in the end of the day, when you do the factorization formula, what's matched here between these two sides is the PZ over C.
Are you saying zeta on the left-hand side is basically set equal to some quantity that depends on X and PZ?
Exactly.
Okay, and then, but to extract, then my next question is to extract the Collins-Soper kernel K. Like, what do you do? Do you vary that quantity on the, you vary PZ around and then try to extract?
You can vary PZ around and take a ratio, and here you go. you got the formula to extract the K.
Okay. Tom has a question.
So somehow like the idea that the time form factor is related to soft factor, kind of like from a physics point of view, seems weird to me. I see what you're trying to say here, but in the perturbative factorization theorems, those Wilson lines can radiate gluons all over the place. And in the time form factor, all that has to be suppressed. So
there is lots of soft gluons around here. Yeah, of course.
This like non-perturbatively will confinements. Okay, I just non-perturbatively because of confinement, might they not be the same thing, or is it just that the same soft factor appears in there?
The same soft factor appears in there. So in fact, there's a motto in the large momentum effective theory, is that there's 2 points. The light cone is not well defined, okay? And in non-perturbative sense, and in perturbation theory, you can do that. Second is that you can always use large momentum to approximate a light cone. And so therefore, you can, this way, you can do your perturbative physics, non-perturbative physics. And so the point here is that I got 2 Wilson line, I need to cook up large momentums to approximate the light cone. And so this is the way that you will see that it will approximate. And you, of course, you need to derive a factorization theorem for this. Okay, so in other words, that you can derive a factorization theorem for the form factors, and you can see that it is equal to the wave functions of one of this, another wave functions, and times the soft factor. So that's how the soft factor arises from here.
And so how do you, so you need to know those wave functions, so.
Oh, yes, you need to calculate those wave functions. Yes, we also calculate those wave functions.
Okay. On the lattice or?
On the lattice, exactly. So your starting point will be calculated lattice wave functions. And this also has a large moment effective theory, which I didn't discuss here. So all the light cone wave functions, the light from quantization theory can be calculated using this approach. So you can complete the program light from quantization without doing any light from quantization at all. That is, you can do the matching and get all the wave functions that Brodsky want to get.
Arthur has a question.
So on the lattice, the extent of that staple-shaped Wilson line is going to be finite. What are the corrections associated with the difference between finite and infinite length staple?
Okay, very good question. So what happens is that so long as this guy is in the vacuum, you're fine. Okay, so basically this, sticks out of the vacuum, into the vacuum. So the good thing is that when the hadron moves very fast, it contracts. And so when it contracts, it means that the Wilson line can very easily get outside of the hadron. So you don't want to be staying inside the hadron. So therefore, so long as the Wilson line is bigger than the size of the hadron, and even less so, and you only need to have like a 1 over gamma to the hadron size. And then you should reach a symptotic region. So when all this construction is done, you can calculate everything as a function of L with the Wilson line. You want to show that when the L gets large and it gets a plateaued as a function of L. So all calculation you have to show that there's L dependence, and then L dependence goes to a constant when L is sufficiently long.
Thank you.
More questions? There's 2 hours till dinner.
Okay. Well, have a great rest of one day, right? You have a one more day, and
Well, I mean, if you don't have any more to add, give the floor. No, I see Young is on the call. You want to add any commentary about other approaches?
Oh, I think it's great that we have come this far in finding solutions for the soft function, which is really the last piece and a crucial piece to enable us to calculate the TMDs. And right now we are working very hard to try to implement this approach on Lattice and to calculate, let's say, the Collins-Soper evolution, and also calculate these spin-dependent TMDs. We haven't started yet, but for example, the Sieverts function that you have great interest in, I think is now, we have the theoretical tools to calculate them, and we should expect first results maybe within a year or two from Lattice. So if you are interested in Lattice calculations of TMDs, this is definitely a great great era, and also there are also many theoretical studies that are still need to be worked out. So yeah, I'm not here to invite collaborations, but anyone who is interested in these issues should find some both challenging but also meaningful questions or problems to solve.
Well, how many postdoc positions are you offering?
Well, it depends on the funding proposals, right? We probably will have a postdoc next year, and this next fall, we can support at least one. But one doesn't have to be my postdoc to work on these topics. I mean, you can simply read those papers and come up with your own ideas and solutions. You don't have to be physically working with us. Yeah.
8 positions help.
Hopefully, yeah.
Let me try to make one comment. That is, I'm gonna write this up into a notes, which I'm gonna distribute. If anyone wanna help me to write this, I really appreciate it. So just send me email, you say you want to help, and then, you know, we can, yeah, I think that a lot of stuff I discuss here, although scattered in papers, but in a way that is sort of explained to people first time hear this in a way that people can understand it easily. It's I think it's probably useful to other people as well.
I think I can help.
Mhm. Great. Send me email.
You have to make them pay you. Well, you can take up that conversation on the Slack channel if you like.